So we'll now look at an example of assembly when we've got symbols. So the first step is to create a lookup table. So we can see the table on the left here contains all the predefined symbols and the kind of numeric equivalent, and then we've left a space at left a blank table at the side for any user-defined symbols, so we can add those in as we go through the code. So in this example, it's a bit longer example, and we can see we've got some user-defined symbols in. So we've got some variables, we've got a loop, we've got a label in there. So we can see we've got a few user-defined symbols in here, so this is a bit more involved to go to assemble. And on the first pass, we're basically just looking through the code and trying to find any symbols, any labels, any user-defined labels. We just add the per to the lookup table, where n is the next instruction number, or the base or line number. So we start on the first pass, we go through the code, we're looking for these labels. We can see we get to this and we come across loop. So notice here, this label doesn't have a line number. You know, this is just a label in the code. It doesn't correspond to an instruction. And the actual next instruction is 4. And then again we can find another. We carry on going through the code. We find another label. So cont, and the next line there is 18. So we just put those into our user-defined symbols list. So we add in loop with line number 4 and cont with line number 18. And on the second pass, so that's all we're doing the first pass. We're just adding the labels to the code. And on the second pass, we go through the code line by line, translate the C and A instructions with literals to binary instructions. But if the A instruction has actually got a user-defined symbol, we need to look in the lookup table, replace it with a numeric value if we do find it. But if it's not in a table, then add it to the table in the next RAM slot. So the user-defined symbols start at 16, remember? So 0 to 15 are taken up by R0 to R15, and then user-defined symbols start at R16. So add it to the lookup table, and then we can replace it by its numeric value and translate to the binary instruction as normal. So in this case, we'll start the second pass, and we've on the first line here we can see we've got @I. So this is a user-defined symbol. We look in the lookup table. I doesn't exist, so we need to add I, and it starts at 16. So remember, user-defined symbols start at 16. So then we know that line will be, so @I actually becomes @16. So it's just a case of, again, putting the A instruction. So we know A's instructions, bit 15 is a 0, and then we've just got the binary value for 16 in here. The next C instruction we just decode as normal. I'm not going to go through that procedure just to save time, but you just decode. Well, we know that for this example, those 3 bits will be 1. Again, there's no jump, so these will be 0. Then you just have to look at the corresponding tables to come up with the values of these bits. But again, we'll not worry about C instruction in this example. The next instruction we get to is @sum. So this is another user-defined symbol. So we add that. It doesn't already exist in the lookup table, so we need to add sum to our lookup table. And now I was at 16, so this one will be at 17. So go back to the code, replace @sum with @17, and then just put obviously the binary value for that in. We just decode the next C instruction as we would do, as we've done before. Again, carry on. Again, we miss, these labels are not instructions to be decoded, so we just ignore those. We go on to the next instruction, which is @I. So we know that I from the lookup table is actually 16, so we can just replace it by 16 and put it in. we'll just miss out these next three instructions. These are C instructions, just decode as normal. The next instruction we get to is @cont. So this is obviously a symbol. We go to our lookup table and we see cont has got a value of 18. So replace that by @18 and just convert it to its binary equivalent. Again, the next one's just a C instruction. We can do that. @I, we know that I is at 16, so we can just put the binary equivalent in. Again, next instruction, C instruction, just decode it as I've done before. @sum, we look in the table. Sum exists in the table and it's got the value 17. So replace @sum by @17 and give it its binary value. Again, this instruction is just a C instruction, decode as normal. I, by now we know is 16, so we can just put the binary value of 16 in. M equals n plus 1 is obviously C instruction, just decode as normal. @loop, so that's obviously the symbol we need to look in here. @loop, so loop has got the number 4, so replace @loop by @4 and decode and just give it its normal binary value. Again, the next instruction is just the C instruction, just decode as normal. So we can see it's not too hard to do this. There's this extra pass where we first find the labels and add them to the lookup table, but after that the procedure is pretty much the same as it was before. So once you've assembled your code, you're going to have this kind of tables of ones and zeros, which is a raw binary machine code. So this needs to be typed into a text file and stored with a .hack extension. So this, this is recognizing that this is a kind of hack machine language, and then we can load that into the CPU emulator tool. Then you can just run, you can run the code in the CPU emulator. But also, there's actually an assembler tool that's provided as part of the Nano Tetris tool suite. So you can also load in the assembler file, so the .asm file what contains a hack machine language. You can load that in, and then you can actually, there's actually tools in there to compare it to your manually assembled .hack file. So you can load in the assembler source file, then load in your manually assembled hack file. So you go file, load comparison file, and as you step through the assembly procedure, the assembler will compare your file to your manually assembled file to the one created by the assembler. So it'll tell you if any errors have occurred, it'll highlight any differences, and you know that you've done your assembly incorrectly.